Hello everyone, welcome to the Mercury Virtual. Hope you are doing good. Today I am going to continue with the same module but the new part, that is a part number 4, that is a transaction management. So the same module, that is a database design concept, but with the new topic, new part, that is the part 4, that is a transaction management. That is how to manage the transaction, or what is a transaction, how to differentiate between the various transactions, what is the criteria to manage the transaction, that is a transaction management. That is a part 4. So let's start with the part 4, that is the transaction management. And in the last class we have also finished with the chapter number 13, that is the last chapter. In this we have talking about the query optimization. Now this is the next chapter, that is the next part basically, that is part number 4, that is the transaction management. So let's start with the transaction management. So first of all, what is a transaction? That refers to the collection of various operations that forms a single logical unit of work. So whenever there will be a single logical work, whenever there will be a single logical unit of work that will be performed, in which the various operations or multiple operations are carried out, that is a transaction. That means performing anything, performing any task, that is known as a transaction. That means refers to the collection of operations that forms a simple logical unit of work. For example, transfer of money from one account to another, that is also a transaction between two updates, each of which or one to each account. That is, transaction means exchanging the two values, exchanging the accounts, exchanging from one account to the another account. That is transferring the money from one account to the another account. It is important that either all the actions of a transaction can be executed completely. That is, it is very important that either all the action that is required, that to be executed completely, that means transaction must be executed in a complete manner, or in case of some failure, partial effects of such incomplete transaction to be undone. This property is known as the atomicity. That means, atomicity means whatever the transaction that is followed, whatever the rule that is followed, that must be finished in a time. That is the atomicity. Further, once a transaction is successfully executed, its effect must persist in the database. That is, once the transaction that is successfully executed, that is successfully done, or we can say the finishes, its effects must persist in the databases. That is, its effect must be present in the databases. A system failure should not result in a database forgetting about a transaction. So whatever the system failure that is available, that does not result in a database forgetting about a transaction that successfully completed. This property is known as the durability. So we are talking about the two properties of a transaction, that is the durability and the atomicity. And transaction means a collection of operations that performs a logical or some logical unit of work. So whenever we perform something, done, that is done in the uniform manner, that is known as a transaction, right? In a database system where the multiple transaction, because there is no one transaction that is executing at the same time, but there are multiple transactions, that means transferring the money, transferring the details, logging out the details, carrying out the details. That means multiple transactions are carried out in a database system. So if updates to share the data are not controlled, there is a potential for transaction to see inconsistent intermediate states that is created by the updates of other transactions. That means whenever there are multiple transactions, wherever there are more than one transaction that is executed, that means that transaction must be executed in a polite manner, or that must be executed in an inconsistent manner. Such a situation can result in erroneous update to data stored in a database. Therefore, database system must provide the mechanism to isolate transactions from the effect of other concurrently executing transaction. So whatever the transaction that is executed, that must be executed in a concurrent way. That is, one transaction after the another transaction, that is in a concurrent manner. This property is known as the isolation. That means isolate from one executing property, that is, one transaction does not interfere with the another transaction, that is, they work in the isolation. Chapter 14, that is the next chapter, that describes the concept of transaction in detail, including the properties that is available in the transaction like atomicity, durability, isolation, and also provides the properties that is provided by the transaction abstraction. So whenever we abstract the transaction, whenever we see the details of the abstraction that is available, we can see the details of the transaction in a effective manner. In particular, the chapter makes precise the notion of isolation by means of a concept that is known as the serializability. That means every transaction must be executed in a serial way, that is, one transaction after the another. First of all, one transaction will be executed, the output will be displayed. The next transaction will be executed, and then the output will be displayed. That is serializability. Then chapter number 5 describes various concurrency control, and chapter number 16 talks about the recovery management. So 14 is basics of the transactions, 15 is concurrency control techniques, and the 16 is recovery management techniques that is available in the database, or what are the various recovery management component of a database. Taken as a whole, the transaction management component of a database system allows application developer to focus on the transaction, that is ignoring the issues of a concurrency and the fault tolerance. So let's start with the chapter number 14, that is the transactions. So first of all, what is a transaction? That is a collection of various operations on a database that is appeared as a single unit. That means, for example, transferring the money, that involves various activity. But we can say transferring the money that involves multiple activities, but the name given is a transaction. That means collection of various components or various operations on a database appear to a single unit from the point of view of the database user. So from the point of view of database user, it is known as a single unit where various operations are performed on a database. For example, a transfer of funds from a checking account to a saving account is a single operation from the customer standalone or standpoint. So whenever we transfer the funds from a checking account to the saving account, that must be done in a single operation from the customer's standpoint, from the customer point of view. It is essential that all these operations occurs, or that in case of a failure, none occurs. It would be unacceptable if the checking account were debited but the saving account not debited. That means proper transaction only be maintained whenever there will be a execution, that the debit must we can say reconcile with the credit. That is the accounts term. That is, if the amount is debited, then the account is also credited. Then only the proper transaction is taken place. Then collection of operation that forms a single logical unit of work, that is known as the transaction. So whenever we collect various operations that forms a single work, that forms a single logical work, that is known as the transaction. So transaction means various operation that forms a single unit of work, that is known as the transaction. Then a database system must ensure proper execution of transactions. Despite failures, either the entire transaction executes or none of it does. So whatever the database system that requires, that must be executed in a proper manner, that must be executed in a despite manner, that is a failure, that is either transaction executes or none it does. So whenever we collect multiple operations that form a single unit, that is known as a transaction. So clearly it is essential that these operations occur, or in case of a failure, none one occur. So whenever the operations are formed within the transaction, that means every transaction must be fully accepted, must be fully operational whenever we collect multiple operations. For example, when we transfer the money, the same amount will be debited, the same amount will be credited from two different amounts or different accounts. So collection of operations that form a single unit of work, that is known as a transaction. A database system must ensure proper execution of a transaction despite the failure. That is, despite the failure, the transactions are executed in a multiple manner. So in case of the fund transfer example, a transaction computing the customer's total balance might see the checking account balance before it is debited by the fund transfer transaction. So suppose if I want to transfer the funds, that means transferring the fund, that means debited the amount. That debit must be done after checking the account. If the account does not have a balance, then how the account will be debited, how the amount will be deducted. So first of all, see whether the amount is available or not for debiting the amount. As a result, it would obtain an incorrect result if the balance is not available and we credit the amount from that account. This chapter introduces the basic concepts of the transaction processing and details on the concurrent transaction and the recovery from the failures are in the chapter 15 and the 16. So this chapter is generally talking about the transactions and what are the various properties of the transactions. So first is the transaction concept, that is a transaction. So a transaction is a unit of program execution that accesses and possibly updates various data items. So what is a transaction? That is a unit of a program execution. That means whenever we pick up the single unit, that is a transaction that consists and that access and possibly updates the various data items. So whenever we access the single unit of a program, that is a transaction that is used to update other items also. Usually a transaction is initiated by a user program that is written in a high level data manipulation language, that is a SQL, that is a SQL, or the programming language, for example C++, Java, which embed the database access in the JDBC or the ODBC. So whatever the content, whatever the data that is required, that is available in the data manipulation language. So the transaction is initiated by a user program that is available in the data manipulation language, that is the SQL, or the programming language, that is the C++ or Java, with the embedded data access in the JDBC or the ODBC, that is the Java database connectivity or the open database connectivity. And a transaction is delimited, or we can say the is terminated by the statements or the function calls of the form, that is the begin transaction and the end transaction. So there are two types that is required, that is the begin transaction and the end transaction. The transaction that consists of all the operation that is executed between the begin transaction and the end transaction. So whatever the transaction that is required, that consists of all the operation that is executing between the current transaction and the begin transaction. This collection of steps must appear to be the user as a single indivisible units. Since a transaction is indivisible, it either executes entirely or the we can say the sum parts. So this requirement holds regardless of whether the transaction itself is failed. If it is divided by that 0, the operating system crash or the computer system stop working. So whenever there are some failures in the computer, for example the operating system fails, for example the transaction itself is failed, for example the operating system crash, or the computer itself stopped operating, as a result this will ensure that the requirement is met is very difficult, since most changes to the database may still be stored in the main memory variables of the transactions. That means still the main memory is required for the computing the transaction. So there are multiple requirements, or we can say that there are multiple failures that occurred in the computer. So in that cases, some may have written to the database and stored on the disk. This all or none property is referred as a or referred to as a atomicity. So whenever we take the property, whenever we apply the property that is taken, that is known as a atomicity. Furthermore, since a transaction is dated, or since a transaction is a single unit, its actions cannot appear to be separated by other database operations. So as we see, ensuring that this requirement is met, it is difficult that some of the changes may be stored in the main memory. So this property is known as the atomicity. That is, everything is possible or everything is fair in the we can say the executing the transaction, so that there is no loophole available in the transaction. Furthermore, since a transaction is a single unit, its action cannot appear to be separated by the other database operations not part of the transaction. So whenever we talk about a transaction that is a single unit, and its action cannot appear to be separated by other database operations not part of the transaction. While we wish to present their user or this user level impression of transactions, we know that reality is quite different. Even a single database or even a single SQL statement involves many separate accesses to the database. That is, there are multiple access that is available in the database, and a transaction may consist of several SQL statements. Therefore, the database system must take special actions to ensure that the transaction operates properly with no interference from the currently executing database element. That is nothing that once a transaction is going on, so the another transaction is affected by the first transaction. No, that is not the case. So this property, or this we can say the facility, is provided by the property of the database, that is the isolation. That means every transaction is an individual transaction, and every transaction works depend on their task, depend on their work. Even if the system ensures correct execution of a transaction, this serves little purpose if the system subsequently crashes, and as a result the system forget about the transactions. Therefore, a transaction's actions must persist across crashes, and this property is known as the durability. That is, the crashes does not affect on the transaction, that is, the crash does not affect on the various database that is available in the database systems. That term is known as a durability. That means durable things are available for accessing the database. So because of the three properties that is available, that is atomicity, durability, and the isolation, and transaction is known as the ideal transaction that is required of the structuring interaction with the database. That is, because of the above three properties, transactions are the very ideal way or the ideal way of structuring the interaction with the database. This lets us to impose a requirement on the transactions themselves. That is, imposing a transactions, imposing a requirement. What is the requirement of the transactions? How to interact with the transactions? What are the various properties that is available in the transactions? And the transaction must ensure, must preserve the database consistency. That is, the database is consistent. If a transaction is run atomicity in isolation, starting from the consistent database, the database must again be consistent at the end of the transaction. This consistency requirement goes beyond the data integrity constraint we have seen earlier, such as the primary key constraint, referential integrity, check constraint, and the like. That is, rather transactions are expected to go beyond that to ensure the preservation of those application-based transactions. And this property is known as the consistency. To restate the above more precisely or more concisely, we require that the database system maintain the following properties of the transactions. These are the three properties of the transaction, that is atomicity, that is a consistency, that is a isolation. So atomicity means either all the operations of a transactions are reflected properly in the database or none are. That means either all the operations are available in a transactions, that is the transaction performs each and every operation, either none operation will perform by the transactions. Then consistency, that is execution of a transaction in isolation, that is with no other transaction executing currently. That means every transaction is isolated transaction. No one transaction can preserve or can affect the other transaction. Then isolation, that means even though multiple transaction is currently executing, that guarantees that every pair of the transaction must be finish their task in a sequence order. We can say in a scheduling order, that is one transaction is executing, then next one, then next one, then next one, that is in a proper sequence, in a proper order. Then there will be a durability, that is after a transaction completes successfully, the changes it had made to the database persist even if the systems are failure, or even if the systems failures can occur. That means the effect on the transactions or effect of the transaction must maintain in a durable way, must maintain for the long time, even if that if there are some error or some failures in the database systems. These are the four properties of a transaction: atomicity, consistency, isolation, and the durability. This property is known as the acid properties of the transaction, that is atomicity, consistency, isolation, and the durability. We shall see later, ensuring that the isolation property may have a significant adverse effect on the system performance also. So let's start with the next topic, that is a simple transaction model. That is how the transaction works. That is a simple transaction model that depicts whatever the transaction that is required. So because SQL is a powerful and complex language, we begin our study of transaction with a simple database language that focuses on when the data are moved from disk to the main memory and from main memory to the disk. In doing this, we ignore the SQL insert and the delete operations. So for doing the simple transaction, we are ignoring the two operations, that is the insert and the delete operations. The only actual operation that is required on the database are restricted in the simple language to arithmetic operations. Later we shall discuss the transaction in a realistic SQL based content with a richer set of the operations. And each data element item is identified by a name, that is A, B, C, D, etc. And we shall illustrate the transaction concept using a simple bank application consisting of several accounts, and that set of transactions are required to access and update those accounts. So there are multiple accounts that is required by the banks, and there are multiple operations that is required in the accounts. And transactions access data using two properties. So there are two properties by which the transaction must acquire the properties, that is a read and the write. That means reading the data from the database to the variable, and write means writing the data into the main memory or writing the data into the main memory buffer of the transactions. So it is important to know if a change to a data item appears only in the main memory or it has written to the database on the disk. In a real database system, write operation does not necessarily result in the immediate update of the data on the disk. Let TI be a transaction that transfer 50 from account A to account B. This is one of the transaction, that is a read A. First of all, there will be a read A, and the A is equals to A minus 50. Then there will be a write A, then there will be a read B, then there will be a B, then write. So first of all, the read will be carried out, then the operation will be carried out, and then write the transaction on the database, that is the write A. In the same way, read out the B, and there will be B equals to B plus 50, then the write B. Let us consider each of the asset properties. For the ease of presentation, we term as the ACID, that is the consistency, atomicity, isolation, and the durability. So consistency means that the sum of the A and B are unchanged by the execution of the transaction. That is, the output is consistent, or the result that is available is consistent. That is a consistency requirement that is available in the A and the B, that must be unchanged by the execution of the transaction. And without the consistency requirement, money cannot be created or destroyed by the transaction. So there is no consistency that is maintained, so no money will be transferred. So ensuring the consistency for an individual transaction is the responsibility of the application programmer who codes the transaction. So whenever we do the operation, whenever we uh, join the operation that is for the single individual transaction, that is the responsibility of the application programmer who codes the transaction. This task may be facilitated by the automatic testing of the integrity constraints. Then next is the atomicity. That means the we can say the different transactions, different operations that will be carried out within the execution. That is, for example, suppose that just before the execution of the transaction TI, the values of the accounts are the 1000 and the 2000 respectively. Now suppose that during the execution of the transaction TI, a failure occurs that prevents TI from completing the execution successfully. That means no one operation will be carried out, and the failure occurred between the transaction. That means the atomicity cannot be maintained. So because of the failure, the state of a system has no longer effect on the real state of the world. We term the such a state as an inconsistent state, in which there will be a problem, there will be a crash that occurs between after the one transaction before the second transaction. The basic idea behind atomicity is the database system keeps track on the old values of any data on which the transaction performs a write. This information is written to a file that is known as the log. So whenever we write any information, that is available in the database in the form of a log. And if the transaction does not complete its execution, the database system restores the old value from the log to make it appear as though the transaction never executed. So if we have made the changes, that is the x equals to x plus 40, then after giving or after going to the right, there will be a system crashes. That means the data cannot be updated or data cannot be changed. Rather than the database system picked up the data, that is first of all, that is x plus 40, that is from the database system, that is from the file, that is from the log that is maintained in the database system. That means recovery system, that is also one of the major tasks that is discussed in chapter number 16. Then there will be a durability, that is once a transaction of the or execution of the transaction completes successfully and the user who initiated the transactions have been notified. So once the transaction successfully completes and the user who initiated the transaction have been notified, then that the transfer of funds have taken place, it must be the case that no system failure can result in a loss of data corresponding to the transfer of funds. We assume for now that a failure of the computer system may result in the loss of the data in the main memory, but data returned to disk are never lost. And protection against the loss of data on a disk is discussed in chapter number 16. And we can guarantee the durability by ensuring that either the updates carry out the transactions have been returned to the disk before the transaction completes. So before the transaction completes, the update must be carried out into the disk. And information about the update carried out by the transaction and returned to the disk is sufficient to enable the database to reconstruct the updates when the database system is restarted after the failure. So whatever the update, whatever the information that is available, that will be carried out by the database system to update or reconstruct the update when the database system is restarted after the failure. Then next is the recovery system, that is also available in chapter number 16, that is the next chapter, that is used for ensuring the durability in addition to the atomicity. Then next is the isolation, that is transaction must be executed in the isolation. So even if the consistency and the atomicity properties are ensured for each transaction, but if the several transactions are executed simultaneously, that is in the concurrent way, their operations may interleave in some undesirable way. That is, their operations must interact with each other in some way that result in an inconsistent state. So whenever the transactions output reconcile with each other, interact with each other, that they affect the result into the inconsistent state. So when we database is temporarily consistent, while the transaction to the transfer funds from A to B is the executing with the deduction to the A. A way to avoid the problem of concurrently executing transaction is to execute transaction serially. That is, one transaction will be executed after the another. That is, the transaction must be executed in a sequence way, in a serial way. That is, they must be executed to perform the operation that is carried out in a transaction that will be taken to ensure that durability is maintained after the execution phase. So therefore they allow the multiple transaction that is to be executed in a sequence way, that is executed in a concurrent way. And one of the major concern that is talked about for the concurrency control system, that is more than one transactions are executed at the same time. Next is the storage structure, that is how to maintain the storage structure, what is the requirement for the storage structure. So to understand how to ensure the atomicity and the durability properties of a transaction, we must gain a better understanding of how the various systems or how the various data items in the database may be stored in the access. That is, how to maintain the database, how to get the database, how to access the database that is available in the database storage. So to understand the atomicity and the durability properties of a transaction, we must gain a better understanding of various data items in a database that may be stored in the access, that is the storage structure. That means the transactions must be updated, or the transactions must be carried out in a database that must be taken out in the various storage media, for example disk, hard disk, floppy disk, and the CD-ROM. So these are the various storage devices that is available for the database system to work upon. That is, the data will be stored in some backup devices that is known as a floppy disk, hard disk, system failure, anything that is used. So we must gain a better understanding of how the various data item in a database system may be stored in the access. In chapter number 10, we stored that the storage media can be differentiated by their relative speed, capacity, and the failure or resistant to the failure. That is, it depends on the storage media, whether whatever their speed, whatever their capacity, and whatever their content that will be available, that is resistant to the failure, and classified as a volatile storage and the non-volatile storage. So the storage media can be classified into two forms, that is the storage media, volatile storage and the non-volatile storage. And we review these terms and introduce another class of storage that is known as the stable storage. So there are three types of storage. One is a volatile, one is a non-volatile, one is the stable storage. Now, first is the volatile storage. So whatever the information that is residing in the volatile storage does not usually survive system crashes. That means volatile memory means whenever the power has gone, the data will vanish. That is a volatile storage. So information residing in the volatile storage does not usually survive system crashes. Examples of system storage are main memory and the cache memory. So there are two memories that is available in the volatile, and we have discussed these memory in detail in the first classes, that is when the new model has not been started, that is the starting of the computing system, that is volatile storage. And how to access the volatile storage, that is relatively fast, because whenever we access the primary memory, whenever we access the cache memory, that is relatively fast as compared to the backup memory, that is a secondary memory, because the speed of the memory access itself is very efficient, and to access the data item is volatile directly. Then next is the non-volatile storage, that is the information that is residing in the non-volatile storage system crashes, or whenever there will be a system crash, that will be carried out by the non-volatile storage. And the examples of the non-volatile includes the secondary storage, that is the magnetic disk, floppy disk, flash disk, also used for the online storage, and the optical media, that is a magnetic tape, magnetic disk, that is also used for the archival storage. At the current state of technology, that is a non-volatile storage that is slower than the volatile storage. So non-volatile storage is very slower than the volatile storage. Next is a stable storage, that is the information that residing in that stable storage is never lost. Never should be taken up with a grain of salt, since theoretical never cannot be guaranteed. For example, it is possible, approximately unlikely, that may be a loophole, that may be a earthworm that will be available in the database storage. That is a stable storage. Although stable storage is theoretically impossible to maintain, it can be closely approximated by the techniques that makes data loss extremely unlikely. That means stable means that is a combination of the volatile and the non-volatile, and the data loss is very less in case of the stable storage. To implement the stable storage, we replicate the information, we duplicate the information in different non-volatile media, that is usually the disk, with the independent failure modes. Updates must be done with the care to ensure that the failure during an update to stable storage does not cause a loss of the information. So whenever there will be update, that must be ensured that the failure does not affect the stable storage media, that is a combination of the volatile and the non-volatile storage. And there will be a concept that is known as a RAID, that is a redundant array of independent disks, that also ensure the volatile storage and the non-volatile storage. Now next is the two properties of the transaction, that is the atomicity and the durability. So atomicity means the transaction must complete their execution, and durability means the transaction must be available, or transaction is available for the long time, that is the updates must be retained in the transaction for the long time, that is a durability. So atomicity means a transaction must complete their execution at the in a successful way, and the durability means the updates must be available for the long time. So a transaction must not be always complete execution. Whenever these scenarios occur, that is known as the aborted transaction. And if you are to ensure the atomicity property, an aborted transaction must have no effect on the state of the transaction. So whatever the state of the transaction, whatever the state of the database that is available, so the transaction does not be affected. Therefore, any changes that the aborted transaction made to the database must be undone. So once the changes caused by the aborted transaction have been undone, we say that the transaction have been rolled back. Rollback means again moving to the same transaction, again going back to the same transaction, that is a rollback transaction. And it is part of the recovery scheme to manage the transaction aborts. This is done by maintaining a log. That means, for example, if I'm doing the transaction for pages 0 to 100, and if my log is available at the 50, and if the par has gone after the 55 page, that means 50 have already been occurred, or already been recovered, because we have placing the log on the 50 page. So the data that is lost for only, that is from 50 to the 55, that is only the 5 pages are lost, and we can recover the data for the 50 pages with the help of the log system. So time to time the logs will be maintained. So there is no hard and fast rule that only one log will be maintained between 0 to 100. No, we can also maintain the log, 4 logs, 5 logs, any n number of logs in the from the 0 to the 100 page. And maintaining a log also provides the possibility of redoing a modification to ensure the atomicity and the durability. That means we can redo the work, we can again carry out the work, that is a modification that is done, that also ensures the durability and the atomicity, as well as the possibility of undoing a modification to ensure atomicity whenever the failure, in case of failure during the transaction executed. So whenever there will be failure during the execution of the transaction, that must be carried out by the atomicity and the durability. And when the transaction completes its execution, that is known as a committed transaction. That means if the system fails but the transaction must, or transaction completes its execution, that transaction is known as the committed. That means commit transaction means the operation, the task that is assigned to the transaction that completes its execution. And the way to undo the effects of a commit transaction is to execute a compensating transaction. So whatever the effect that will be available, that will be available in the undo stage, that will be used to execute a compensating transaction. For example, if a transaction adds 20 to an account, the compensating transaction would support 20 from the account. It is not possible to create such a compensating transactions. And we need to be more precise. What do we mean by the successful transaction of a, or completion of a transaction? It is not that I'm saying that my transaction is successfully done. That is not okay. So there are some attributes, there are some properties, there are some rules that will be carried out whenever we say that the transaction is successful completed transaction. So we therefore establish a simple abstract transaction model. A transaction must be going from the following states. If the transaction must be going from the following state, or we can say it will carried out the following state, then only we can say that the transaction is a successful transaction. So the first state is active state, that is the initial state, that is the transaction state, or we can say the occurs in this state while it is executing. That means while the current transaction is executing, that means the active stage. Then the partially committed, that is the partially committed means after the final completion has been executed. Then failed, that means there will be some error in the database, error in the system, that is not required. Then there will be aborted, that the transaction is aborted for some time, that means like a pause for the some time, that will be restored to the previous or the state prior to the state of the transaction, and committed after the successful completion. So whenever the transaction will be successfully completed or executed, that means that is a committed state. And this diagram shows how the transaction will appear in the transaction management. We say that the transaction has committed only if we entered the committed state. This is the state diagram of a transaction. First of all, there will be active, then there will be a partially committed, then committed. In a partially committed, it may be going to the failed, and there will be aborted transaction, that is going on the going on the transaction phase. So this is the active, then there will be partially committed. From the partially committed, there will be a failed transaction, there will be a committed transaction, there will be a aborted transaction. So this is the state diagram of a transaction. In the similar way, we can say that a transaction has been aborted only if it has entered the aborted state, and is terminated if it is either terminated or the aborted. And the database system then writes out the enough information to the disk that even in the case of the failure, the update if performed by the transaction can be recreated when the system restarts the failure. The next topic is the transaction isolation. So let's come back from the break. Let's start with the session. So as the name advised, that is a transaction isolation. That means one part is connected, not connected with another part. That is a transaction isolation. So transaction processing systems usually allow multiple transactions to run concurrently. That is, multiple transactions must be allowed to run concurrently in a similar way, in a singular way. That is a concurrent execution, or the concurrent. We can say the concurrent concurrency. That means multiple transactions must be executed at the same time. To allow the multiple transactions to update data concurrently causes several complications. So whenever we execute the transaction in a concurrent way, that causes several complications with consistency of the data, as we saw earlier. Ensuring consistency in spite of the concurrent execution of the transactions requires extra work, and it is far easier to insist that the transactions run serially, that is one time or one at a time, each starting only after the previous one has been completed. That in a sequence order, that is a more than one transaction. If multiple transactions are executed, that is only one transaction is executed at the same time. In a serial way, multiple transactions are executed, that is only one transaction at a time is provided the benefits, provided the resources. So there are two reasons, or there are two good reasons for allowing the concurrency. So whenever there will be concurrency, that means multiple transactions are concurrent uses. That is, the first one is improve the throughput and the resource utilization. That is, whatever the output that is give or that is executed by the multiple transactions gives a better output as compared to the single transaction. And the next is a resource utilization. That is, the proper resources are utilized. That is known as the resource utilization. A transaction consists of many steps. Some involve input-output activity, the other involves CPU activity. The CPU and the disk in a computer system can operate in a parallel. Therefore, the input-output activity that is done in the parallel with the processing at the CPU. And the parallelism of the CPU and the input-output system are therefore be exploited to run the multiple transactions in the parallel. And whatever the system, whatever the operation that is executed on the read or the write terms, that is increases, or that increases the throughput of the system. That is number of the transactions executed in a given amount of time. The next is the reduce the waiting time. So first one is improve the throughput, then reduce the waiting time. So whatever the wait time that is required by the transaction, that is reduced, that is reducing the waiting time. There may be a mix of transactions that is running on a system, some short and some long. And if the transactions run serially, a short transaction have to wait for a preceding long transaction to complete. That will lead to the unpredictable delays that is available in running a transaction. And if the transactions are operating on a different parts of a database, it is better to let them run concurrently. That is, concurrently means multiple transactions are executing at the same time. Moreover, it also reduces the average response time, that is the average time for a transaction to be completed after it has been submitted. So it also reduces the average response time that is available to complete the transaction. The motivation for using the concurrent transaction or concurrent execution in a database is essentially the same as the motivation for using the multi-programming. So whatever the concurrent transaction that is available, that means more than one programs are executing at the same time. That is a multi-programming in the operating system. Then, this is the most important line: when various transactions or when several transactions run concurrently, the isolation property may be violated. That is, the isolation property may be disturbed or the violated, that results in the database consistency being destroyed despite the correctness of the each individual consistency. So whatever the consistency, whatever the database, whatever the operation that we want, that must be destroyed, that must be not used whenever there will be a correct or instead of using the correctness of the individual transaction. In this section, we present the concept of schedules to help identify those executions that are guaranteed to ensure the isolation property and therefore provide the database connectivity. And database connectivity means provide the database connectivity connection that is available in the database concepts. The database system must control the interaction among the concurrent transactions to prevent them from destroying the consistency of the database. It does do it does so through a variety of mechanisms that is known as the concurrency control scheme. So there will be a scheme that is available, that is a concurrency control scheme that is used for the concurrent transactions, that is used for the concurrent method that is used to prevent them from during the consistency of the database. This is one of the example. Consider a simple banking example, that is read A minus 50, write A, read B, B plus 50. So which has several accounts and a set of transactions that access and update the transactions, like T1 and the T2 are the two transactions. And for T2 that transfer the funds from one account to another, T1 transfer the $50 from account to the B. Now transaction 2 transfer 10% of the balance from the account A to the B. This is the next one, that is a transfer from the A to the B, that is a 10% only, that is a A into 0.1. Then A is A minus 10, then write, then read B, then B is B plus 10. That means one is subtracting, one is adding. This is A is subtracting, that is debited, and the B is adding, that means credited. Now, what are the trends in the concurrency? That is, whatever the trend, that is, we can use a multiple processor for the concurrency control. For the concurrency, that is, more than one processors, more than one CPU are used for providing the concurrency among the transactions. And for a database system to take advantage of multiple processor and the multiple cores, two approaches are being taken. One is to find the parallelism within the single transaction or the query. Another is to support a very large number of concurrent transactions. And there are many service providers that is also providing or that is also using the large number of computers rather than the mainframe computers to provide the services. Suppose the concurrent or the current values of the account, that is the A and B, are the 1000 and the $2000. Suppose that the two transactions are executed at the same time, that is ordered by the T1 that is followed by the T2. So first of all, T1 transaction is carried out, then only the T2 transaction will be carried out. And that must be available, or that must be followed in a chronological, or we can say the chronological order, that is from the top to the bottom, with T1 appearing in the left column and the T2 appearing in the right column. This is one of the method, that is T1. So first of all, the T1 is commit, that is finish the execution, then only the T2 begins the execution, that is a commit. That is schedule 1, that is a serial schedule in which the T1 is followed by the T2. Similarly, if the transactions are executed one at a time in the order T2, that is followed by the T1, then the corresponding execution sequence is that of the figure 14.3. Against as expected, the sum A plus B is preserved and the final values of the accounts A and B are the 850 and the 2150 respectively. This is the serial schedule in which the T2 is followed by the T1. So first of all, T2 is taken place, then only the T1 is taken place. The execution sequence thus describes are known as the schedules. That means scheduling the transaction, whatever the transaction that is used, that means schedule the transactions that is carried out in the serial way. So the transactions also maintained in a serial way, that is the transaction will be controlled by the serial way. That is known as a schedule. And whenever we say that schedules are the serial, so whenever there will be a serial schedule that consists of a sequence of the transactions from various transactions, that means the transactions have a sequence. The sequence will be maintained for the transaction that will be carried out, that will belong to single transaction that appears in the another transaction. So when a database system executes several transactions concurrently, the corresponding schedule no longer needs to be serial. So whenever it will execute in a concurrent way, so no longer schedule or the corresponding schedule no longer will be required as a serial way. And if the two transactions are running concurrently, so if there are two transactions that is running concurrently, the operating system may execute one transaction for a little while then perform a context switch, execute the second transaction for some time and then switch back to the first transaction for some time and so on. That means switching from one transaction to other transaction whenever there will be a requirement for transferring from one part to the another part. The next point says several execution sequences are possible since the various instructions from both the transactions are interleaved, and the final stage that is occurred at the inconsistent stage. And there will be also control that is provided by the concurrency control component of the database system that carries out that there will be a proper control like this one. So first of all there will be a T1, then after T1 there will be a T2, after T2 there will be a T1, then again T2. That means one transaction is carried out only the read operation and the write operation. One is carried out for the write as well as the read operation. Then again read B. That means T1 and T2 is allocated for the transaction A, and the T1 and the T2 is allocated for the transaction B also. That is the concurrent control. That is at the same time the concurrent control will be carried out. This is the serial way, that is the serialized way, that is in the serial order. Next is the serializability, that is whatever the concept that is provided that is also available in the serial way. So before we can consider how the concurrency control components are carried out, we can ensure that the system also ensure about the serializability. We consider how to determine when a schedule is serializable or the not. So when I say a schedule is serializable or not, that is also one of the main concept that is carried out in the concepts of the transactions. So serial schedules are serializable, but if the steps of a multiple transactions are interleaved, it is harder to determine whether a schedule is serialized or not. So it is very difficult to determine whether the schedule that is available in a sequence order or not. That is, one transaction is executing, then another, then another, then another. So in this section we discuss different form of sequence or schedule equivalence, but focus on a particular form that is known as the conflict serializability. Let us, let us consider a schedule that is S in which two consecutive instructions, that is the I and J of transactions, that is the Ti and the Tj is available. And this is one of the serializability, that is the first of all there will be a read queue, then there will be a read queue, then the order of I and J does not matter since the same values of Q is read by the Ti and the Tj regardless of the order. And I equals to read Q and the J equals to write Q. It comes if I comes before J, then Ti does not read the value of Q that is written by the Tj in the transaction. Then I equals to write Q, read Q, that is order is also provided for the database systems. And this is the graphical representation of the serializable order, that is how to represent the graph in a serial way. This is a topological sorting will be available. This is the topological sorting, that is a Ty, Ti, Tj, Tk, Tm. And Ti, J, K, M, that is it is available in the sorting order of the we can say the alphabetical sorting order. And returning to the previous example, note that the precedence graph for schedule 1 and 2 in read do not take or do not contain the cycle. So whatever the cycle that is available, that does not contain the cycle in the content manner. Then next is the transaction isolation and the atomicity. That is transaction isolation is also available in that is also carried out. We have discussed about the transaction isolation and the atomicity. Now these are the various concepts, or these are the various subsections that will decide what are the various schedule that is accepted from the for the recovery point of view. So first is the recoverable schedule. That is a schedule will be recovered, or that will be a recoverable schedule. In this we are also using the partial schedule, that is not included commit or the abort transaction for the T6. Then there will be a cascade less schedule, that is if the schedule is recoverable, to recover correctly from the failure of a transaction, then we have to roll back the transactions. That schedule is known as the cascadable or cascadal or cascade less schedules. Then next is the transaction isolation levels. That is what are the various levels that is available in the transaction isolation. So what are the levels? One is the serializable, that ensure that the transaction must be executed in a sequence way, that is a serial way, that is a serializable. Then repeated or repeatable read, that only committed or that also allow only committed data to be read, and further requires that between two reads of data by a transaction, no other transaction is required to or allowed to update it. Then next is the read committed, then read uncommitted. So one is a repeatable read, then read committed, then read uncommitted. All the isolation level is describe or disallow the daily or dirty writes. Then implementation of the isolation level, that is how to implement the isolation level. There are various properties, there are various concurrency control policies that we can use to ensure that even when the multiple transactions are executed concurrently, only the acceptable schedules are generated, regardless of how the operating system time shares resources among the transactions. So regardless of the concept how the time is shared among the various resources, the operating system time shares resources among the various transactions. And transaction requires a lock on the entire database before it starts with the or before it starts and releases the lock after it has committed. A concurrency control policy such that this one leads to the poor performance if it forces transaction to wait for the preceding transactions. Next is the locking, that is instead of locking the entire database, a transaction could instead lock only data items that it accesses. That is, instead of locking the entire database, it is a better approach to lock the each and every individual item that is required, that is data item that is accessed, that is locked, instead of locking the entire database. And also locking also ensures the serializability, but for a period short enough not to harm the performance excessively. And further improvements to locking result if we have two kinds of locks, that is the shared and the exclusive lock. Shared lock means that is lock is also shared, the password is also shared, that will be accessed by only the specified person. And exclusive lock means that is only the owner can use the lock, that is the exclusive lock. So shared locks are used for the data that the transaction needs and or that the transaction reads, and the exclusive logs that the transaction writes. That means for writing purpose there will be exclusive log, and for reading purpose there will be a shared log. Then there will be a timestamp. That is also another category, that is how to implement the isolation. For each data, the system has two timestamps. The reads timestamp, that it holds the largest timestamp of those transaction, that is the data item, and the write timestamp that hold the timestamp of the data but wrote the current value of the data item. That is reading the data item, that is the timestamp, then writing the data item. Then multiple versions and the snapshot isolation. So that comes in the serialization view, that is how to map the transaction, how to view the multiple versions and the snapshot isolations. Then the transactions as a SQL statement. So whatever the transaction that is available as the SQL statement, that is used in the SQL transactions. So next is the transaction is also used as the SQL statement. So there are SQL statement that is available for using the transactions. So we have presented the SQL syntax for specifying the beginning and ending of the transactions. Now that we have seen some of the tissues or some of the issues that is used in ensuring the acid property, that is atomicity, consistency, isolation and the durability. In our simple model, we assumed a set of data item exists. While our simple model allowed data item values to be changed, it does not allow the data item to be created or deleted. In SQL, however, insert statement creates a new data and the delete data or delete statement deletes the data. So whenever we use the insert, that means inserting the data. Whenever we use the delete, that means deleting the data. And these two systems are in fact right statement since they change the database by their interaction with the action of other properties. For example, consider the following query with the university database that finds all the instructor whose salary is more than 90,000. So select ID name from instructor where salary is more than the 90,000. Using our simple instructor relation, we find that the Einstein and the Benson satisfy the relation condition. Now assume that around the same time we are running our query, another user inserts a new instructor, that is a name James, with a salary that is a 100,000. The results of our query will be different depending on whether this insert comes before or after the query is sent. So this is one of the important tasks. So before executing the query, the new name will be added. That means the output will be displayed with the new name also. But if the name will be added after the query is executing, so there will be a conflict, that is the name will not be available at the out or in the output. This situation is referred as a phantom phenomena because the conflict may exist on the phantom data. Our simple example of transaction that is required, that the transactions must operate on a specific data item that is given as the argument to the operations. There are two operations that is used, one is the read and the write steps. And one of the best way to deal with the transaction, deal with the problem, that is to recognize that it's not sufficient for the concurrency control to consider only those tuple that are accessed by the transaction. The information used to find the tuple that are accessed by the transaction must also be considered for the purpose of concurrency control. Now, next is the predicate locking, that is we can log the data, we can log the content that is available in the predicate contents. Then next is the summary, that is a summary of the chapter. So a transaction is a unit of a program execution that accesses and possibly updates various items. That is a unit of program that is available in the data items. And this is a property that is used for the transaction, that is the ACID property. So next is the second point is that transactions have the ACID property that is used, that is the atomicity, consistency, isolation and the durability. So these are the four ACID properties that is available of the transactions. And atomicity ensures that either all the effects of a transactions are reflected in the database or none are reflected in the database. Then consistency, that ensures if the database is initially consistent, then the execution of the transaction leaves the database in a consistent state. Then isolation, next is isolation, that ensures that the concurrent or concurrently executing transactions are isolated from one to the another. That is, whenever there will be a concurrent execution of the transaction, that must be isolated from one form to the another form. Then durability, that ensures that once a transaction has been committed, that transaction must be updated, do not get lost of the data in case of a system failure. The next point is concurrent execution of a transactions improves throughput of a transactions in the system utilization and also reduces the wait time. Then the various types of storage are available, like volatile, non-volatile and stable storage. And stable storage must be accessible online. Next point is when several transactions occurs or executes concurrently in the database, the consistency of data may no longer be preserved. And there will be a serializability, that is a conflict serializability and the view serializability. And we can test the given schedule for the conflict serializability. Then schedules must be recoverable to make ensure if the transaction A sees the effects of transaction B and the B then abort, then the A get also abort. That is the schedule. That is a one transaction, one we can say the transaction must be aborted to the next transaction. Then next is the concurrency control management, that is also available for handling the concurrency control policies. So we are finished with the chapter number 14 also, and these are the various practice exercises. And now let's start with the next topic. Let's start with the next chapter in the next class, that is in the Monday's class, that is chapter number 15, that is a concurrency control. So let's start with let's stop the class over here only. If there is any doubts, any confusion, you can ask the doubts from me. And in the next class, that is in the Monday's class, I'm starting the next topic, that is chapter number 15, that is a concurrency control. So that's all for today's session. Thank you so much everyone for listening me. Bye bye everyone.